Okay, let's look at the 2006 Form B AB free response question. We have a table of values. We have a car traveling on a straight track. They tell you that the velocity and acceleration functions are continuous. One thing I don't like is they didn't mention differentiability, but particle motion is differentiable, barring weird situations. Um, Okay, so part A, use appropriate units to explain the meaning of this definite integral in terms of the car's motion, and then approximate that using a trapezoidal sum. Well, this definite integral, the area under the absolute value of velocity, is a total distance. Okay, so that integral will represent, how shall I type it? I'll write it. So the antiderivative, whoops, lost my pen, from 30 to 60 of v of t, and now I'll type. Represents the total distance in feet. You always want to include units, and they tell you to use appropriate units. Total distance in feet. The car travels on the interval 30 less than t less than 60. So when you are giving explanations and they ask you to include units, first they shouldn't have to ask you to include units. That should be automatic. What they didn't ask you to do is include the interval. You want to restate everything that is part of the setup. So that definite interval does represent total distance traveled. And then for the second part, to approximate that with a trapezoidal sum, we're going from 30 to 60. And they structure trapezoidal sums so that you have unequally spaced intervals. And for the trapezoidal sums, remember the area of a trapezoid is 1/2 the height of the trapezoid times the sum of the bases. And the height is the delta x's, which are inconsistent. We go from 5 to 15 to 10. And the bases are the function values. Okay, so this one, my first trapezoid goes from 30 to 35. So that's 1/2. The height of that trapezoid is 5. And the bases are -14. I'm sorry, we're using velocity. So my function values are -14 and -10. But do remember we're doing the absolute value, which I forgot right here. And so the bases will be +14 and +10. Then we'll move on to the next one. 35 to 50 is a height of 15, and the values of the function are -10 and 10, but the absolute value of that, -10 and 0, would be +10 and 0. And then my last one from 50 to 60, a height of 10, and absolute value does not come into play here. The velocity values are 0 and 10. Absolute value remains 0 and 10. And on the AP exam, you are absolutely allowed to stop right there. So you could just write feet and quit. However, if you do want to clean this up and get a simplified answer, this does end up equaling 185. However, there's no benefit to doing that. You can only risk making it wrong if you do choose to simplify that. So let's go on to part B. Another using appropriate units explain the meaning of that. And so let's explain that meaning. And this is a weird one. I kind of did a double take on this question. But if you were to evaluate this, which we will, it does say to find the exact value of this, we would start by finding the antiderivative, which would be the velocity. Actually, I'm going to answer the second part first. So if I find the antiderivative of acceleration, that would be the velocity function from 0 to 30. That is how you do exact answers for definite integrals. You find the antiderivative, then you evaluate it from upper limit to lower limit. And we could get the exact value this time because we have the velocity at 30 and we have the velocity at 0. So the answer is going to be -14 minus a -20, which ends up being a +6. And so there is the value. Now to explain the meaning of that, so 0 to 30 of a of t, what we ultimately did when I evaluated that, I subtracted the values of the velocity. So this is the change in velocity. And the units would be, because we are measuring velocity, feet per second on the interval 0 to t to 30. And so since I did just establish units, I'll go ahead and slap units up here in my numeric answer, which I actually did the second part before the first part. So there's part B. Looking at parts C and D of this question, both of these are theorem questions. So the first one says, is there a time for which velocity is equal to -5? And when I see something like that, notice it just directly says velocity. My first thought is intermediate value theorem, which is applicable because the function velocity is continuous. And so all I'm going to do is try to see anywhere that I would have to cross -5. And I see that right here because at 35, my velocity is -10. At 50, my velocity is 0. I have to hit -5 somewhere on that journey. And so to explain that, and I'm going to type this to make this a little bit quicker. I'm going to use the intermediate value theorem. And to use the intermediate value theorem, you have to establish the conditions that allow you to use it, which is that the function is continuous. Now, I realize that they have already said that, but you probably need to say it in your explanation as well. So first I'm going to say velocity is continuous on the interval 0 less than t less than 60. Then I'm going to lay the groundwork to that establishes the intermediate value theorem works, and that is at 35, my velocity at 35 is equal to -10, and really the important part is that that is less than -5. I want to tie it to the value I'm trying to achieve. So my velocity at 35 is less than -5, and my velocity at 50, which equals 0, is greater than -5. Therefore, the intermediate value theorem guarantees that v of t equals -5 for some t on the interval. And I'm going to narrow it down. They asked for the interval 0 to 60, but I'm going to narrow it down to 0 to 50, which is inside 0 to 50, 0 to 60. I don't know what I'm saying. Did I say 0 to 50? 35 to 50. Anyway, I just discovered that I have a hard time typing and talking at the same time. So velocity is continuous. We want to reestablish conditions for the theorem. I established that the velocity is less than -5 at one point and greater than -5 at the other. Therefore, intermediate value theorem guarantees that velocity equals -5 somewhere on that interval. Okay, so looking at part D, which is almost identical to part C, very, very similar question. Must there be a time when the acceleration is equal to 0 and justify your answer? So my first thought, because I have a row of acceleration values, is to try the intermediate value theorem just like I did in part C. However, looking across your acceleration values, you notice that every one of them is positive. There is no forcing me to hit 0 by using the intermediate value theorem. So since that failed, I'm going to go a different route. And I will say that usually, this isn't always the case, but usually when they ask a yes or no question, must there be a time when something happens, or does the function ever do this? Usually it's yes. Doesn't have to be, but usually it's a yes. So since the intermediate value theorem is not forcing it to happen, I'm going to go a different route. And the different route is I'm going to change my thought process from acceleration to the derivative of velocity. So does the derivative of velocity equal 0? And when I think of it that way as a derivative question, it changes my focus, because if you're ever asked to guarantee that the derivative equals something, start with the mean value theorem. So start with the mean value theorem. And in this case, this would be specifically Rolle's theorem because the derivative needs to equal 0. And to use the mean value theorem, your function needs to be differentiable and continuous. This is where I don't like this problem because they tell you the function's continuous. They never say explicitly that velocity is differentiable. However, the only way we can answer this is to make that assumption. And so we're going to use Rolle's theorem. And in order for Rolle's theorem to be conclusive, we need the slopes equal 0. We want to find two values from 0 to 60 where the slope between those two values is 0. And I usually start by going from the beginning to the end. However, if I measure the slope from 0, -20 to 60, 10, I will not get a 0. So since comparing my beginning and end values was inconclusive, I'm now going to look somewhere in the interior. And because I want the slope to equal 0, I need the y-coordinate to be the same at two different places, and that happens at 0 and 25. So if I'm going to explain this or justify this to College Board satisfaction, you start by laying the groundwork for whatever theorem you're going to use. So I'm going to use the mean value theorem. And so I would start by saying velocity is continuous, and differentiable on the interval 0 to 60. That's a 6, not a 60. On 0 to 60. Therefore, the mean value theorem guarantees. Oh, wait. You know what? I'm going to go a little bit different because I'm not using 0 and 60. I'm using 0 and 25. So I'm going to say that V of 0 is equal to V of 25, and they both equal -20. Therefore, and we could use mean value theorem. I'm going to go more specific, and I'm going to say Rolle's theorem says that V prime of t, which is acceleration, and I'm going to tie it to acceleration specifically because that is how the question was originally worded. Therefore, Rolle's theorem says that the derivative of velocity, which is acceleration, must equal 0 somewhere on the interval 0 to 25, and there is your explanation for that one.